is sorting and searching algorithms. And let me share my screen really quickly. 1 second. Okay, I hope you see my screen. Please shout if you don't. So today we're gonna see that sorting and searching algorithms that sound quite scary at the beginning are not that scary at all. And let's start with searching first. So searching is actually something that we all do every day, right? Just remember this character from Soul movie, where she's trying to find a record in her database. She's basically scanning all the records in search for one that she really needs. And this is what searching is all about. So the task for search is, given some array or collection of items, of elements, we need to find a specific item and say, where is that located? Or if it's not in the collection, we need to say, sorry, it's absent. How to approach this problem? There are multiple solutions, namely linear search, hash search, and probably at this point you should recall hash maps from the previous session, binary search, and also many others. But let's start with easy stuff, linear search. So imagine we have this array of 10 elements, and we have a really easy task to find 37. So naive linear approach would be, guess, yeah, it would be just scanning through all the array. So we check first element. Is it 37? Nope. We proceed. Is it 37? Nope. We continue further. Still nope. Okay, we found it. So we found this element 37. We'll return, sorry, not 4. We'll return 3. Yeah, that's a typo. We'll return 3. Let's try to find 1. We know already that there's no 1, but let's see how algorithm will find out. So we start with the first element, 0. Is it 1? It's not. Then we scan all of them until 5th one. Still haven't found it. We continue scanning until the end of the array. Still not found it. And then array is over, element not found, we return -1, because obviously -1 is an invalid index. So that's a good indicator that we haven't found anything. So the code, all the code today will be in Python. So apologies in advance for people who code in other languages, but I still hope that this is understandable. The code is really simple. It's just a linear search function. We pass an array of interest, we pass length of the array, and we pass the number of interest. And then we just iterate and compare one by one all the elements with the object of interest. If we find it, we return the current index. If we don't find it, we return -1. So obviously, since we have to traverse through each element of the array, time complexity would be linear, right? Because at most you will always have to scan like the whole array. I hope that was easy start. So please.
Right, so did you say, hello, my dear.
Hello.
Monica here. Did you say this is like Python? You're doing it in Python?
Yeah, this is Python.
It's very similar to Java.
It is, but Python does not require classes and stuff.
No,
so you can just like create functions. Yeah.
Yeah. Much more easier, I think.
Yeah.
Sorry, just for George Lane.
Yeah, no problem. Yeah, no problem. So, okay, I guess like that was an easy start. So let's move forward. Binary search. Can we do better than just linear? Seems like it's not very efficient thing. Yes, we can, turns out, but we need to do some preparation. Namely, we need to sort our array first. So think about it as of, let's say, a book, or better yet, a dictionary. So imagine you are trying to find a translation to some word, maybe a dog. You don't know how dog will be in Spanish, right? So how humans proceed this task? They just open a book on a random place, and you're seeing that you opened it at letter O. You know that D is less than O, so you need to open like earlier pages. So again, you open it random place and you see now the letter is C. Okay, C is less than D, so you need to like rotate further. I think it's pretty much obvious. So this is exactly the way how binary search works, actually. So let's consider this example. So we have our array, but it's now sorted, as you can see. We want to find number 37 again, but instead of starting on the leftmost element, we start right in the middle. So we have 10 elements. So number 9 minus 0 is 9. 9 divided on 2 is 4. So we start at the middle. Is it 37? No, it's not. 37 is smaller. So we know that we should not search in here. Instead, we should search in there, in the left one, in the left side. So we say, okay, on our next iteration, we're only looking in the left part of the array. And the next element that we'll be looking at will be element number 2, because 2 is in the middle of interval from 0 to 3. Sorry, yeah, it's actually 1, because like 3 divided by 2 is 1. Yeah, so we're looking 35. 35 is not 37, right? 37 is bigger. So now we know that we shouldn't be looking in the part of the array that's bigger than 4. We know that we should not look in the part of the array that's smaller than 1, right? So this leaves us only these 2 elements. What's in the middle of these 2? The middle is this element. And finally, we have found 37. Again, exactly how you would look for a word in a dictionary. Let's see what happens when we're trying to find an element that doesn't exist in this array. So let's try to find, let's say, 91. We already know that 91 isn't here, but let's see how algorithm will find it out. So again, we start like with the whole array, and middle is at number 4. And again, 45 is not 91. 91 is bigger. So now we concentrate on the right side of it. We're moving to the right interval. Now we're looking at the middle of the right interval, and it's 55. 55 is not 91, and it's smaller. So we need to continue further to the right. Again, we're looking at these 2 elements. This is the middle. 67 is not 91, so we need to continue to the right. Continuing to the right, now our interval consists just one element, and 90 is not 91. So we're trying to do precisely this. We're trying to move our left to the next element, and then what happens? Left is to the right of the right. No, this would not work. So we return and we say, no, we haven't found it. This is how code is looking like. It's actually pretty short. So let's have a look at iterative approach on the right side. So we pass array, we pass left and right elements, right? The left and right arrows, which will be 0 and 9 respectively at this example. And then we provide x, which would be, let's say, 40 again. So what happens? While our right arrow is still to the right, so it's not like this, but rather it is like this or like this. So meaning that we have a valid interval. We find a middle. Then we compare if an element at the middle is the element that we are searching for, we return the index. Otherwise, if we see that current element is bigger than the element of interest, then we move our, let me scroll it, then we move our right arrow to the middle here. And then otherwise, we are starting to search on the right-hand side. Does it make sense? Please leave comments on the chat. Let me double check the chat if I can open it. Okay. Just like, okay, I see one yes. From 0 to 10, how frustrated you are right now? Just let me know. Silence. Okay, the right side of 10 is 0. Okay. Okay, cool. Then let's move on. Then so the binary search that we just revisited. Time complexity of binary search is log n, which is much faster than linear thing. But again, remember, your array must be sorted before you can use it. Memory complexity, it depends on which method you're using. You can use either recursive method here or iterative approach. The difference is that here you have a cycle with while, and here you're just calling binary search function from binary search. The only difference would be in memory, because in iterative implementation, you don't need additional memory, while in recursive one, you use stack when you're calling the function. So the last but not least, search, and we will touch it only briefly, will be hash maps, because obviously you can insert all the data you have to the hash map, and then you can search it really quickly by just calculating the hash and going to the hash map and checking if it's there or not. So time complexity would be normally constant time, but in the worst case, when you have collisions in your hash map, that would be linear. Obviously, because you have multiple elements at one key. So you actually have to go through all of them again, and that would be our first naive linear approach. So what else to mention? Obviously, it's like not a comprehensive list of search algorithms. There are many, many others. And I think like one of them that's worth mentioning would be using probabilistic data structures like Bloom filters. This is a quite interesting data structure that is more memory efficient than a hash map, but there is a price to pay. Since it's probabilistic, it tells you if the element is definitely not in the set, or maybe it is in a set. So sometimes it will say something like, yes, it is in a set, but it's not in there. So, but that's again a price to pay. So moving on to sorting now. We discussed binary search. We said that our array should be sorted before we can use binary search, but how do we sort? And more importantly, do we need to know all these algorithms for sorting? Maybe there's just like one brilliant that always works faster than others. But see this visualization? Seems like not that cool. So I haven't noticed any algorithm that would beat all of the others in all the cases. Some of them work faster in some cases. Some of them work slower all the time, like selection algorithm. So seems like we don't have a clear winner. Each sorting algorithm has its advantages and disadvantages in different situations. So whenever you're choosing which algorithm to use, you always need to take into account first the nature of the data. You see, the data can be random, can be nearly sorted, can be reversed, can be few unique, or like other situations. And also sometimes maybe you have memory constraints. Sometimes maybe you have constraint on how many swaps during sorting you can perform. But let's continue and explore these algorithms. So sorting algorithms can be divided, can be classified by these parameters. First of all, first important bit, computational complexity on best, average, and worst case scenarios. Then memory usage. Some sorting algorithms require additional memory, some do not. Computational complexity of swaps that I just mentioned. Some of the sorts require more number of swaps, bigger number of swaps. Some of them have a thing named stability. By the way, let's discuss what stability is. So sorts can be stable and non-stable, which means stable sort will preserve the original order of equal elements. So you see 5 hearts and 5, I guess it's spikes, but yeah, I'll call it spikes. 5 hearts was coming earlier than 5 spikes, and the order is still preserved. While not stable sort will not guarantee that they will preserve their positions, and probably it will swap them. Well, it doesn't also guarantee that it will always swap them, but it's just a possibility that it will. That thing is also important in certain situations to take in considerations. But again, let's start. The first sorting algorithm that we start with is a bubble sort. Bubble sort actually behaves like a bubble. The element that's been currently sorted is behaving like a bubble. You iterate through an array, you swap elements if they're in incorrect order, and as a result, on each iteration, your biggest element will float to the end, or like to the upper end, like a bubble, literally. And repeat until no swaps performed, but better to look at it instead of discussing it. So let's take a look. So imagine we have this nice array. Let's try to sort it. And something is happening. You see, it goes, and every time it compares two elements. And if the elements are in incorrect order, the sorting algorithm just swaps them. And now we have the highest element of the array on its position in the end of the array sorted. So indeed, like a bubble, it just floats above and it takes its place. And so it just goes on and on and on until there are no swaps. So let's make it slightly faster. Maybe like already here. So yeah. As a result, we will get fully sorted array. This is not modified thing. So yeah, it was modified. So it saw that there were no swaps at the last iteration. So algorithm stopped early. So what happens on the best, average, and worst case scenarios? On the best case scenario, bubble sort will perform in just linear complexity, in linear time, because it will only scan the whole array once. It will not perform any swaps, and it will know that if there are no swaps, no need to continue. So it will stop. On average, and on the worst case scenarios, it will always take n square. So not that good type of sort. It doesn't require any additional memory. It is stable because it only, again, swaps elements when they are in incorrect order. When to use? Well, don't. That's a good sort to start with because it's easy to understand, but it's not really efficient and there are much better solutions. Although having said that, I must mention that bubble sort is used in some work with graphics. There are a few situations when bubble sort actually outperforms other sorts, and mainly it's in some thing with pixels when it's just like few pixels to swap, and yeah, then bubble sort outperforms other sorts. But let's move on. The next sort we're going to discuss is named selection sort, which is also simple. At each iteration, you find the smallest element in the array and put it at the beginning. And that's it. So literally imagine how you're taking something and you just like put it in the beginning, But again, let's take a look. So selection sort. Let's sort it. We're scanning the whole array. And currently we think that number 3 is the smallest element. Now we think it's 2 because 2 is smaller. Okay, we're taking 2, putting it at the beginning. Then again, scanning for the smallest element. Currently it's 5. Now it's 3. Okay, finish scanning, moving 3 to the beginning. Scanning again, and yeah, it will find 4 and put it at the beginning, and then just iterate and continue. So in the end, it will be sorted again. So now we have a nice sorted array. What do you think the complexity is? Well, I mean, since we again have loop inside the loop, we have linear complexity on the already sorted array because we will only scan once. Then we have on average again n square, and on worst case we also have n square, and our space complexity is 1 because it constant, sorry, because we don't need any additional space for that. We just mixing and matching different elements. Again, when to use when input data is almost sorted because it works quite fast, and when swaps are costly. In general, it is faster than bubble sort, so prefer it to the bubble sort. But again, this sorting algorithm is not the best in terms of average and worst. So let's continue to others. But before we do that, just like take a look at the code. You see, it's again pretty straightforward. We just scan all the time, and we find the minimal element, and then we swap it with the current with the one that's like at the beginning of the array currently. So moving on, insertion sort, another easy to understand algorithm. So we have an array which is already split in two parts. There's sorted part, which is empty at the beginning, and unsorted part, which is like the whole array at the beginning. During each iteration, next element that you take, you find a proper place for it in the sorted part. Let's take a look how it works. Insertion algorithm. So let's start sorting. So at the beginning, we mark the first element as the sorted one. The next element would be 44. Okay, 44 is bigger than 3, so we leave it as its place. Look what will happen with 38. We select 38, then we're trying to find a proper place in our sorted part. It should be here because it's smaller than 44 and it's bigger than 3. We insert it. Okay, moving on, number 5. We're trying to find the proper place for it. 5 and 44. Okay, 5 should go to the left. 5 and 38, still should go to the left. Okay, 5 is bigger than 3. We finished, we can insert. And then continue similarly. So I guess it's also easy for understanding. And yeah, we can see how it works. And of course, again, we would have a complexity of n squared because you see we are iterating on the whole list twice. First, we're scanning like for the next element, and secondly, for each element, we're scanning back. So that's why n squared. Yeah, so again, in the end, we would have a fully sorted array. So that's when should we use it and when does it perform good? Again, on an already sorted input, average n squared, space doesn't require any additional space. When to use? When input is small and is almost sorted, and number of swaps is not important because selection sort performs less number of swaps than insertion sort. And as you can see, the code is again pretty simple. So we just move elements that are greater than the current key to the position, to the proper position. That's it. Now we're going to move on to two cooler algorithms, but they are also kind of slightly harder to understand. So one of my favorites is named merge sort. So as you can guess from the name, we will always merge some parts of array. So how does it work exactly? Imagine we have this array, and I'm also hoping that you see my cursor. So the first element would be, we will divide the array on two parts, on two halves, and we will start with the left part of it. So left part includes 70, 50, 30, and 10. Then again, we split the array, and we have two parts, 70, 50, and 30, and 10. And then again, we would split, so that in each half of the array, we will have only one element. What happens next? We have the 70 and 50, and we merge them. We know that 50, we're comparing 70 and 50, so 50 is smaller than 70, so we put 50 first, and then we put 70. Similarly, we do with 30 and 10. We know that 10 is smaller than 30. We'll put 10 first, then we'll put 30. Now it's time to merge these two pairs. We compare 50 against 10. 10 is smaller. We put 10 first. Then we compare 50 and 30. 30 is smaller. We put 30. And then we just append 50 and 70. Similarly, we do on the right side with the right half. And in the end, we would have these two halves of the array sorted. So we have 10, 30, 50, 70, and we have 20, 40, 60. We compare 10 versus 20. 10 is smaller, we put 10. Then 30 against 20. 20 is smaller, we put 20. 30 and 40. 30 is smaller, and so on and so on. And then we result in a sorted array. Let's take a look at the visualization. Again, it's maybe not the best one, but still, I hope it will also help. So you see, we have split the array on like elements, like until there's only one element in each split. So now we have 3 and 44, and we compare them. They already sorted, so we put them back, and now they are of the same color because they are merged. So next would be 38 and 5. We compare them, we merge them, they're merged. They're both yellow now. Oh, orange, sorry, not yellow. Yeah, now we're trying to merge these two. So we take 3, then we take 5, then we will take 38, then we'll take 44. Okay, this part is merged as well. Now it's all red. And similarly, we proceed until the end. So this might be a little bit tricky to understand. So again, please let me know how frustrated you are from 0 to 10 right now in the chat. And if it's hard to understand, I will try to slow down and explain in the other way. Okay, 0, good. Not frustrated, good. I like it, thank you. So, okay, so complexity-wise, merge sort outperforms the sorts that we just discussed before it, because on best, average, and worst case, it always works as n log n, but also it does have its own disadvantages. First of all, merge sort requires additional space. You need the space for the merging, right? So because it's not swapping, it's actually, you see, it's always like creating new arrays, and it's like result append, result append, result append. So it will always require additional space. Secondly, if you remember previous sorts, they performed better on the best case scenario. So previous sorts, they were smart about the array that's already sorted. Merge sort will not do that because it doesn't have an early stop. Merge sort would always split array and then merge it again, even when it's already sorted, unfortunately. When's the best case to use it? Sorting linked lists, because as opposed to array lists, we can insert items in the middle in constant time, and then without using additional space. Moving on to another sort, which is going to be the last one for today. It's a quick sort. It slightly resembles merge sort, because again, we would be splitting our array, but it still is slightly different to the merge one. So if you remember, on the merge sort, we would always split current array on half. With quick sort, it chooses an arbitrary element, which is named pivot. So pivot can be first element, it can be last element, it could be median, or even random element. So how it looks precisely. So we have our initial array, then we select, let's say, last element of the array as pivot. Then we iterate through all array, and all elements of the array that are smaller than pivot, we put it to the left side, and all elements that are bigger than pivot, we put to the right side, right? And then again, we just continue. So we're taking this left side, we take last element as pivot, so it's number 1. Again, we scan whole part of the array. Whatever is smaller than our pivot, we put to the left. Whatever is bigger, we put to the right. And then continue until we have only one element in each part. And then again, we merge. So it's going to be -6, -3, 1, 2, 5, 6, 8, 9. That's it, basically. So let's, again, take a look at the visualization. Highly recommend this website. So it selects first element as a pivot. So we split it. There was like only one element that was smaller. So now this part is sorted. So now our pivot element is 38. So whatever is smaller than 38 would be green part, and whatever is bigger than 38 will be violet part. And then iterate until everything is sorted. And already sorted elements are marked as orange because they are already in their place. We know that for sure. So basically that's it. And the complexity of this algorithm would be n log n on best case. On average, it's also going to be n log n. On worst case scenario, though, unlike merge sort, it could be n square complexity. Why is that? Well, for each pivot strategy, there are so-called killer sequences. So like array with a very bad sequence for this particular algorithm. So what happens when you provide killer array to the quicksort? The partition process will always pick greatest or smallest element as pivot, which will then eliminate all the benefits of splitting, right? You'll be always sourcing like 1, 1, 1, and that will be basically working just like selection sort. Remember selection sort when you always pick the smallest element, right? And this would happen exactly the same way in here. So, but it does beat merge sort on space complexity because again, it does not require any additional space. So to sum up, we have discussed a couple of algorithms, and since I see we still have time, maybe we will touch base on heap sort as well right now. So this is a good table comparing the algorithms on the time complexity and space complexity. And again, as you can see, there is no clear winner. There is no sort that clearly outperforms everyone else on both time complexity and space complexity, even like on any cases. So areas to grow: heap sort that we will discuss now, parallel sorting. It's like basically when you can sort your array on multiple machines in parallel. Sorting when data doesn't fit into memory. That's another interesting case because all the sorting algorithms that we just discussed, they require all the data to be loaded to memory. And maintaining the sorted order in trees and tries. So I actually always struggle with pronouncing this. I don't even know how to pronounce it properly. So maybe let's discuss real quickly the heap sort then, since we have time, unless we have questions. Oh, thank you, Dot. So let me just like open this white screen and let me try to draw some stuff in here. So another sort. I did not realize that we will be so quick today. So another sort is a heap sort. So heap is actually an interesting data structure. Why is that? Because heap always has elements not exactly sorted, but all these elements always fulfill one condition. The element above others, the element that's above the others is always smaller than others. So let's say this is going to be a heap, but it's not sorted, as you can see, right? Maybe, let me see, maybe it will be 117 because I can. And then maybe this. So it's not exactly sorted, right? If you start pulling data from it, it will be like you take 2, you take 3, you take 10, you take 117, then 21. Doesn't make sense, right? But you always know that this, like 2, is smaller than everything else. Then you know that 3 is smaller than its children. Then you know that 10 is smaller than its children, and stuff like that. So heap always guarantees that. How does it guarantee? Well, basically, heap is working in a way when, imagine you want to insert new element. Let's say we want to insert 1. And obviously, 1 is smaller, right? So we want to insert it. Then what will happen? The heap will have to rebuild itself. So it's going to be number 1 on the top. And then everything else will be rebuilt. Probably it will look like this. It will look like 3. And then look like 21, depending on the algorithm that you pick, and then 117. So the heap still preserves. So operation of rebuilding the heap is log n, basically. And then when you want to sort your array of n elements, you'll need to insert n times, right? And this n times will be taking log n. Log n time to rebuild the heap. So the heap sort will take this amount of time. Again, that will be best, worst, and average. What's good about it? It doesn't require additional memory because essentially how heap is presented in the memory is just an array again, right? So, and the magical trick is only in indexes because you have, you can always find the child or a parent by indexes. And I might be struggling with the formulas for this. So maybe, maybe, I don't know, Helen could help me in this because yeah, like from just from my memory, I cannot remember it, but yeah, something like, so you have it 1, no, you have 0, 1, 2, let's try to recreate it, 3, 4, 5. Yeah, division is not my best, is not my strongest skill, but yeah, basically that will look like 2, 3, 10, 117, 21, 31, 32. Yeah, and that was like extra. We didn't have it. So yeah, if you're trying to find like this element or like find its children, it's gonna be something like, I guess, 5 minus 1 divided on 2. Yeah, something like that. So the parent would be index of element minus 1 divided on 2, and you can always find like left children and right children, like similarly you can just like deduce the formula to do it. So we can also see visualization. Let me just like figure out how to close it. Okay, cool. We have our heap sort here. No, we don't have heap sort here, unfortunately. Yeah. Oh wow, how do I close it? How do I clean it? Clear all drawings. Cool. Okay, cleared it. So yeah, I hope that was helpful to know. So yeah, heap sort is like actually one of my most favorite sorts. And yeah, as a bonus, we could also take a look at this magnificent playlist. I don't know if you have seen it before or not, but yeah, let's take a look at selection sort. So I don't even know if that will share the music. Yeah, despite
you have to when you share the screen, you have to click a checkbox, share the sound.
Okay. I wish I could see it. Okay, I found it. Cool. Does it share now?
Yes, all good.
Okay, cool. So yeah, these guys are trying to show how the selection sort work. And as you can remember, selection sort is the one when we pick the smallest element and then we put it in the beginning. So I guess that guy, like with number 0, he will be the smallest. And now he's comparing himself against everyone else. Well, yeah, they will continue. And like, since he is the smallest, he will eventually take his place. So now second element, which is 3, right? She'll be also comparing herself against everything else in order to find a smaller element. So yeah, they found the 1, and then she'll be dancing here because she's the smallest apparently. And then after she compares herself with everyone else, she will take the first place. So yeah. Okay. I actually don't know why it's like going faster because I didn't do anything. I guess it's just like the video itself. Yeah, cool. I guess maybe we can wrap up, maybe discuss like maybe if you have questions, and then we can move on to the practice time because we have 3 carefully selected LeetCode questions for today. Yeah, shows how slow the sorting also is. It is.
Okay, thank you all. The theoretical part of our presentation is finished, but stay with us. We are going to proceed to breakout rooms as usual and practice some practical exercises.